Good morning, everyone. My name is Kamontira Vishai from Suratnari University of Technology. Today, I would like to present the development a method to generate a Fourier atomistic model of amorphous polystyrene and prediction of mechanical property. Polystyrene is an aromatic hydrocarbon polymer that's made from the monomer styrene. The properties of polystyrene are clear, hard, brittle, and have a low melting point. It is one of the most used plastics. It can be used as protective packaging, container, bottle, tray, and in the making of models. The scale of its production being several million tons per year. Atomistic molecular simulation of polymeric materials has been developed few decades ago to study static and dynamic properties of polymer melt and glass. For larger side chain, polystyrene require large computational resource for structural generation and relaxation. Therefore, an important step toward molecular simulation of this polymer is to find a way to reduce the computation cost. To solve this problem, the closed-gain model is one of the efficient methods for simulation of many polymeric systems. This method usually involves grouping the several atoms into closed-gain bits, which interact with each other through effective potential. Then, the calculation of the structural and dynamic properties at atomic level can be done by reverse map from closed-gain bit to atomistic model. But for larger side chain polymer such as polystyrene, there is no report from anyone yet. In this work, we are interested to employ the closed-gain model to investigate the structure and dynamics of both isotactic, atactic, and syntactic polystyrene melt, and Fourier atomistic model from the reverse mapping procedure to determine their material properties. This is an overview of my work. I will start with map the polystyrene with different tacticity into closed-gain bits, and then performing Monte Carlo simulation, and reverse map from closed-gain bit to Fourier atomistic model. Finally, the structural, dynamic, and material property results can be determined compared with experimental results. The first step, closed-gain model of polystyrene chains. The closed-gain model of polystyrene chain has been performed by grouping one repeating unit of two carbon backbone into one bit. The difference in configuration of benzene ring has been shown in different color, point in and point out. Then map the closed-gain bit on the second nearest neighbor diamond lattice, which have high coordination number and high computational efficiency. After that, Monte Carlo simulation has been performed. The Monte Carlo simulation is based on Metropolis Monte Carlo method. For every Monte Carlo step, single bit and multiple bit moves were tried randomly, and every bit was attempted for both moves. Metropolis criteria was applied to determine whether the move made or not following this equation, where delta E is energy difference between new and old conformation, which includes both short and long-range interaction. If the energy decreases, that move is accessed, but for the energy is increased, we will using the random number between 0 to 1 to determine whether the move is successful or not. For the short intra-chain interaction, is obtained from rotational isomeric state, RIS model. In general, the RIS model for vinyl polymer can be represented by 6 statistical metric weights, for each one with different configuration of side chain. In each statistical metric weight contains the energy parameter, and energy parameter represents the interaction between each group. For polystyrene model, we used the method of Yun et al. In 1975, and the energy parameter shown in here. The long-range interaction are obtained from decrease from the Lennard-Jones potential. For long-range interaction of styrene monomers, we use the Lennard-Jones potential parameter tabulate for toluene to estimate this interaction. At simulation temperature 600 Kelvin. The epsilon and sigma shown here. And only the first T shell of interaction parameter were used to speed up the simulation and also shown in here. The simulation box contains 14 chains of 42 bits of polystyrene at 600 Kelvin with 90 million multicolor steps. Relaxation of the initial structure is needed to decrease the system energy and can be monitoring using the orientation autocorrelation function, which is defined using the end-to-end vector of polymer chain. The rotational motion of syntactic polystyrene from an initial value to almost zero within 90 million multicolor steps, while atactic and isotactic relax to 0.3 and 0.6 respectively. The average mean square displacement of the center of mass, or MSD, also have similar trends, which have the diffusion rate of polystyrene with different tacticity is generally ordered as IPS, APS, and SPS respectively. The last process is convert from closed-scan bit to fully atomistic. The coordinates of carbon and hydrogen atoms in the chain were created after reverse map back onto the diamond lattice. Energy minimization of selected snapshots was performed using zero view with PCFF force field. Then, analysis in structural, dynamic, and material property of polystyrene with different tacticity. In the results and discussion, after reverse mapping but before energy minimization, the distribution function of CC bond torsion angle is confined to discrete state at positive God, tan, and negative God in 60, 180, and 900 degrees. But for the during energy minimization, the torsion angle can move off lattice and become continuous distribution, as shown in the black plot. For comparison, it is apparent that the conformation of atomistic polystyrene chain can be located at minus Gauss state, which quite different the prediction of RS model, which have only zero value. This effect may be consequence of the non-bond interaction due to the phenyl ring that are not present explicit in RS calculation. The cohesive energy can be calculated from the difference between total energy of microstructure and the isolate parent chain. The square root of cohesive energy divided by molar value can be represented to solubility parameter. The calculated solubility parameter of polystyrene with different tacticity can be shown here. And results show that different tacticity has no significant difference in solubility parameter, and this result quite close to the experimental range. The Newton scattering curve can be obtained from Fourier transform of radial distribution function. The amorphous polystyrene with different tacticity have no significant difference. 3 peaks at 0.9, 1.3, and 3.1 are fit to the experimental very well. For the mechanical property, during simulation of amorphous cell under external applied stress, the shape and value of the shell can be changed, thereby enabling the internal stress of the system to match the externally applied stress. The fundamental relationship between the state and strain tension can be shown in this equation, where C is the stiffness coefficient metric. The stiffness metric can be obtained from second derivative of potential energy following this equation. For isotropic material, only through independent coefficient, the Lamé constant, can fully describe the state strain behavior. The Lamé constant can be used to determine Young modulus, Vao modulus, shear modulus, and Poisson ratio following this relationship. For the results of mechanical property parameter, the calculate mechanical property parameter of each polystyrene with different tacticity are quite different, but when compare the atactic polystyrene with the experimental result, it is close together. So, in conclusion, the technique for a multiscale molecular modeling of amorphous polymeric materials is demonstrated for polystyrene with different tacticity. The dynamics at molecular level of polystyrene are quite sensitive to tacticity and can be qualitative ordered as IPS, APS, and SPS respectively. Structural and mechanical property can be determined from the atomistic model, from the reverse mapping procedure, and many material properties are reasonably agree with the experiment. Thank you.